Welcome, everybody. We're going to talk about weather today, and specifically something called the SKEW-T diagram, which is a fairly obscure way of plotting what's going on in the atmosphere at a place and time. And what I hope to convince you is that learning how to access and use these things can unlock some insight into what's going on with the weather around us at any particular point in time. So it's you might think it's a dry subject, but as we'll see, it can be quite a rainy subject as well. The jokes will just keep coming.
There we
Uh,
go. It's one in a row. Good. Let us know.
yeah, I'll try. Yeah, I'll try to wave. Okay, so what are we going to talk about today? What is a SKEW-T and why? How can you generate them for yourself or find out both what's happening currently and what will happen in the future according to computer models? How do you interpret these things, which is the important stuff? And then where can you learn more if I haven't bored you to death with this presentation? Along the way, we'll also get a little bit of physics out of the way. So we'll be reviewing ideal gas law. We'll be reviewing atmospheric stability, which, as we'll see, is a big driver of a lot of the weather that we see around us, particularly when it comes to thunderstorms, very popular in the summer. So what is a SKEW-T and why do we care? So a SKEW-T diagram, as we'll see, it is a representation of what's going on in a vertical slice of the atmosphere. So just think about starting where you are right now. If you could send a probe all the way up through the atmosphere above your head at a particular wherever you are, either in the past, currently, or in the future, it is a way to just on a graph show a rich amount of information about what's happening in the air above us at a point in time. When we see a SKEW-T diagram, it could be a literal actual measurement from a balloon, and we'll talk about balloons in a little bit. Because balloons are sent up at different places around the world and the United States, it could be an interpolation between two balloon sounding. It's called, when you send a balloon up, it's called a sounding, which is borrowed from the nautical term of sending a lead weight down to the bottom of the sea to see how deep the water is. With an atmospheric sounding is the same, but it's sending a balloon up to see what's going on above us. So it could be an interpolation between 2 points, or it could be a prediction because these soundings are fed into the computer models that you might be aware of that are then used to generate weather forecasts. If we know how to read these things, we can do a few things. We can understand a little bit better about what's going on with our own local weather. There'll be times when we can actually make better predictions than the TV or even your favorite weather app. There are lots of times when the local weather forecast will tell us there are going to be thunderstorms, and we can look at a SKEW-T and it's like, no, that's not going to happen. Or conversely, it is going to happen, just as an example. And we can bore our friends at parties, which is, of course, the main reason for doing these talks. So before we dive into the SKEW-Ts themselves, let's do just a quick bit of remedial physics, nothing too fancy. The first thing we need to remind ourselves of, as I'm sure you all remember, is our ideal gas law, which says that pressure times volume of an ideal gas is proportional to temperature. PV equals nRT, if you remember the full formula. And the atmosphere is close enough to an ideal gas that this applies. What does that imply? Well, first of all, if we take a packet of gas and we heat it up, it's going to want to expand if we leave the pressure constant, or if we try and constrain it, if we put it in a jar and heat the jar up, the pressure is going to go up. I think we're all familiar with that. When it does expand, if we allow it to expand, I have the same amount of gas, the same number of gas molecules, but now in a larger volume. So by definition, the density of that packet of gas decreases. And when it decreases, we get buoyancy. So hot air rises. We're familiar with that. The second thing to remember, and this is where the ideal gas law doesn't help us, is that real air contains water vapor. And it's the interplay between the amount of water vapor in the air and its dew point and condensation, those processes that drive a huge amount of the weather that we see around us. So we need to understand a little bit about water vapor and what it does. The first thing to remember is that warmer air can hold more water vapor and colder air can hold less water vapor. To simple way to visualize that warmer air is less dense. The molecules, air molecules are further apart. So there's more room, if you like, for water molecules to fit in between the air molecules. The surprising fact, you might think that humid air is denser than non-humid air because it feels heavy, but actually it's not. Humid air is actually lighter, is actually less dense than the equivalent of drier air. And the reason, if you think about it, a molecule of H2O, single oxygen and two little hydrogens, is less dense than two molecules of oxygen joined together, or or two atoms of nitrogen joined together. So a sort of counterintuitive fact is that all other things being equal, a more humid air is less dense than less humid air. The other really important thing that happens in the process of so if we have air that contains some water vapor and I cool it down, at some point it becomes saturated. It can no longer hold that water vapor, and that vapor condenses into clouds or rain or fog, either droplets. Those droplets can then potentially freeze and turn into snow. But as we cool a packet of air that contains water down, eventually it's going to reach its dew point. That's the point at which the temperature at which the water is going to condense. And the final point is that this the transition between liquid and gas has latent heat of condensation, latent heat of evaporation. And when if we cool a gas and water condenses out of it, that releases heat. And that's a super important process when it comes to creating thunderstorms, which is what we'll see towards the end of this talk. The reason all of these processes are important to understanding what's going on in the atmosphere, and they are sort of writ large when we actually get to the point of the talk, which is the SKEW-Ts. So hopefully that is all just refresher, and everyone knows this from prior lives. So let's actually get to the SKEW-Ts and the observations. A sounding, so this is the actual measurements of the atmosphere, are conducted all over the world twice a day at 1200 UTC and 600 and basically 6 a.m., 6 p.m. Universal Time, essentially Greenwich Mean Time. Radio balloons are launched all over the world, about 800 locations. There are still 92 in the United States locations that balloons are launched from. 69 of those are in the continental US. I think 13, if I remember rightly, are in Alaska, and the rest are like Puerto Rico and the Pacific. So all over the world, these balloons are launched. They are helium balloons. You can see a picture on the right-hand side. So these helium balloons are launched twice a day from these 800 or so locations. You can see a picture on the right of one being released. They go up to about 100,000 feet, and then the balloon bursts. And the payload, which is this little package of sensors that you can see bottom right, is released and comes down on a parachute. You can see the orange parachute in the top photograph here. At least the ones in the US actually contain a mailing bag, and they can be returned to the national NOAA, the National Oceanographic and Atmospheric Administration. Some of them actually are returned, some are not. But as they float up, they broadcast what they're sensing. And what they're sensing is their altitude, their position using GPS, and the local temperature and dew point as they rise up through the atmosphere. So that's the raw data that provides SKEW-Ts. There's actually a fun website you can check out called sonderhub.org, and you can see live all of the radio sondes that are flying around the world right now and exactly what they're viewing, what version of software they're using, which satellites they're talking to. It's kind of a fun site if you're interested in nerding out about radio sondes. So we get these raw readings, and we have to plot the readings somehow. And that's where the SKEW-T diagram, which is the star of today's talk, comes from. So this is what the background of the graph looks like. So let's just walk through this element by element, and we'll gradually layer on more and more information. And they look a little bit intimidating when they're fully populated, but if we break it down, it's not that hard. So it is a graph. Let's start with the y-axis. The y-axis shows pressure, usually in millibars. So roughly 1,000 millibars is 1 atmosphere. So ground level, we're at roughly 1,000 millibars. And as we go up in the atmosphere, the pressure decreases. But it decreases exponentially. And so the y-axis is a logarithmic axis, which means that the altitude is roughly linear. So that's helpful. So roughly at 500 millibars, we're at about 18,000 feet approximately. And obviously that varies day to day, but we just care about measuring pressure at this point. At 5,000 feet, we're at about 850 millibars. The graph helpfully shows the equivalent in thousands of feet on the right-hand side. So you can see this pressure altitude 1, 5, 10, 15, 20 on the right-hand side, corresponding to different pressures on the log scale of pressures on the left-hand side. There's that. The x-axis is weird. The x-axis is temperature. So we can see the temperature in Celsius in the red numbers across the bottom. 0 is freezing or 32 Fahrenheit. 10 is about 50 Fahrenheit, 20, 30. But what makes this graph particularly weird is the fact that the temperature lines are tilted 45 degrees. And that is simply a graphing convention. And because the atmosphere gets colder generally as we go up, if we were to draw this on regular graph paper, these graphs would be incredibly wide and quite short. And so in order just to make them conveniently printed on reasonable shapes of paper, they skew the temperature axis by 45 degrees to the right. And that's what gives the graph its name. The formal name for the graph is a SKEW-T log P graph. SKEW-T, the temperature axis is skewed 45 degrees, and log P because the y-axis is the logarithm of the pressure. So this is the graph paper that we're drawing on. We've got no data on here yet. This is just the background. We then even further complicate things by adding a whole bunch of other lines on it, which are useful to help us discern different atmospheric processes. And we'll get into some of these as we go through the talk. There is these blue lines that run from top left to bottom right are called the dry adiabat, and they are to do with how dry air that is not saturated, changes temperature as it gets lifted in the atmosphere. There is something called the moist adiabats that have to do with how saturated air behaves when we lift it up. And we'll come to these in a little bit. And there's something called the isohumes, which join areas of constant humidity, which we're not going to talk about. And then finally, because this isn't complicated enough, and remember, there's no data on here. This is still just graph paper, right? We sometimes generally show the winds as well at different altitudes, which is important if you're a pilot, but it's also important if you want to help understand what might be going on with the winds that can drive thunderstorm behavior, because certain types of wind and certain vorticity, spiraling of winds are things that can set off giant thunderstorm cells and tornadoes. So the wind is shown in different ways. This graph on the right-hand side can show us wind speed and direction. Sometimes it gets shown on there's a fancy name that is escaping me for a minute for the diagram on the top left. But here's what it all looks like with some actual data on it now. And I've taken off the adiabats and the isohumes just to make this a little bit simpler. So this is an example, our first example of actually seeing a real SKEW-T graph. The different tools produce slightly different variations of these, but they all kind of look a bit like this. They have the features of this. Let's just quickly look at those, and then we'll get into how we interpret them. There are always at least two lines. So in this graph, we've got a red line and a blue line going up on the main body of the graph. The right-hand line is the temperature that's being observed or predicted, and the left-hand line is the dew point that's being observed or predicted. And so this is an example from Bedford, so it's from Hanscom on the 4th of January, 2024. And we can see, for example, looking at the bottom of the red line, that the temperature at 14 Zulu, so this is 9 a.m. On the 4th of January 2024 was about 2 degrees Celsius at the surface, and the dew point was a little bit below freezing. And if we were to send a balloon up at this point, it would rise up, and at about 1,000 feet or so, it would drop below freezing. It would get a bit colder. The line then goes to the right between about the 800 millibar and the 700 millibar level. That's not actually getting warmer, but it is paralleling the -10 degree line. So the temperature is stable. It doesn't change for that little part of time. And then it starts to get colder again. And then the temperature stabilizes again at about the 300 millibar, which is around 30,000 feet or so, which is pretty common in the winter that we see the temperature stabilizing above about 30,000 feet. That's where the what's called the tropopause starts. The right-hand side shows me the wind speed and direction. The blue line going up on the right-hand side shows me the wind speed. And then all of these little barbs and feathers are another way to show wind speed and direction. The way to read this is the barb points into the wind direction. So for example, if we look about halfway up the diagram, there's a red flag pointing to the bottom left. That means that at this 20,000 foot level, the wind is coming from the southwest. If we go up to the top of the chart, it's coming more from the west. And then the feathers and the triangle tell me the wind speed. And the way to read this is that a long line represents 10 knots of wind, and a short line represents 5 knots of wind, and a pennant is 50 knots. So it's for example, right at the top of this chart, we've got 45 knots of wind. Right below it, we've got 50 knots of wind. Below it, we've got 60 knots of wind, a pennant, a triangle, and a long bar. So this shows me my wind speed and direction as we climb up. Okay. So how can you can actually get these yourself. These are free to generate. There are tools online that you can produce your own SKEW-Ts if you're so inclined. There used to be a really nice tool that the NOAA themselves had, which had a lot of really good features. Unfortunately, it was taken down a year or two ago. I would love to say it was budget cuts. I think it was actually just the technology was incredibly old and they could no longer support it. So among many things that are going on, I don't think that that was a particularly political decision. But anyway, it no longer exists. There are some private sites that do it. Some of them are free, including this one. It's called flytheweather.com. And it allows you to generate your own SKEW-Ts, present or future. And there are some other ones as well that I'll give you the links to later on. But to use this, we need to use airport codes because this is a tool for pilots, but it's free. You can put the date and time, and it will then produce the charts that most of the charts that you'll see today have been generated using this tool. So that's one way that you can get your own SKEW-Ts. So, all right, that's exciting, but why? What can we tell? How do we start to interpret these things? And there are 4 broad sets of things that we can tell. Some of these are mostly important to pilots, and I won't spend a lot of time on them, but some are important to us ground dwellers as well. And that's what I'll spend a bit more time on. So those are clouds and fog. We can see not only whether it's likely to be cloudy, but also how high are those clouds are likely to be, how thick they're likely to be, whether they're likely to produce rain or not. We can predict whether those clouds are going to have ice in them, which if you're going to fly through them is very important. We can tell whether they're going to be bumpy or not. And we can most critically, but also most sort of the more sophisticated interpretation of these diagrams can tell us a lot about the likelihood of thunderstorms in a particular area. And that's what we'll spend a bit of time on as well, talking about. So clouds and cloud layers, how can we determine that from SKEW-Ts? So here's another SKEW-T that we can see. Ignore the purple line on this diagram. We're just going to focus on the red and blue lines for now. But here's an example where this is May of this year, also here at Hanscom. And we can see it was 20 degrees Celsius, about 68 Fahrenheit. Nice day at the surface, and a dew point of about 12, so not too humid at the surface. But as we climb up, we see the temperature and the dew point converge. So that air is getting quite a bit colder, and it's getting more humid. And at some point, at about 7,000 feet or so, those two lines converge. And so we know we're going to get clouds at that level because the temperature and the dew point are the same. So all the way, and in fact, they stay converged all the way up through about 16, 17,000 feet if we look at where those lines start to diverge again. And so this is a cloudy day. We can see that it's going to be pretty dark and gray because those clouds are 10,000 feet thick. So we can just immediately see that from this diagram. The other thing that we can see from the same diagram and those same clouds is that above about 10,000 feet, the temperature drops below zero. And this graph helpfully puts this light blue shading to the left of the 0 degree Celsius skewed line. And so if I were flying a small plane, I'd be very cautious. I might be able to fly in clouds, but I'd be very cautious about flying much above 10,000 feet in a small plane, unless I was in the kind of plane that could quickly climb to 25 or 30,000 feet, meaning a jet or a turboprop or something like that. But if you're in a small propeller powered plane, this would be a day to stay low down below the clouds, or maybe, at around 8 or 9,000 feet. So this is a way there's pilots we can tell whether there's likely to be ice in those clouds or not. Any questions on any of this so far? Does it all make sense? Everyone asleep?
You're good, Adam.
Okay, cool.
I have a quick question. Can you hear me?
Yes, yes.
Um,
Hey, Bob.
I was just wondering, um, so I'm in Lexington. It's lately when I look north, I can see a lot of clouds. I don't know how far away they are. I don't know, 10, 20 miles. But here it's sunny. And if they get close enough, they're still sunny, but it rains. So I'm just wondering if the balloon is only checking one spot. How do they, does this take into account, what it's like a few miles away? And yeah, I could get rained on even though it's sunny or
Sure. Yeah, so you're right. The balloons themselves are only in a few spots. There's one that usually goes up on Cape Cod. And it's actually not going up right now because they lost their launch site and they're trying to move it to Chatham. So at some point there'll be balloons again off Cape Cod. And there's another one at Bangor, and there's another one on Long Island. So Bob, in the scheme of things, those are like pretty widely spaced points. um, but all of that then gets fed into computer models that can interpolate between places. So you can get pretty good soundings for any point that you specify. Um, but you're right. What you're going to see is not, oh, there is a specific cloud over a specific spot. What you're going to see are the conditions right that we're likely to see this kind of weather at a particular place and time. Um,
but I was
now,
wondering, it's sunny where I am
mhm.
and but I'm getting rained on. I mean, it's not often, but it happened to be Monday. Um, and so I just
Right. So that's likely to be a day with convection, where the atmosphere is in a state of kind of turmoil because it's maybe being heated somewhere. And we'll talk about convection in a little bit. And one of these
okay.
things, what these diagrams show very clearly are the conditions where convection is likely to happen. And that can be unpredictable in terms of is it literally raining in your yard versus your neighbor's yard? But they can be very, very accurate in terms of, broadly, are we likely to get puffy clouds? Are we likely to get rain or rainstorms or thunderstorms in a particular area and at what time?
Okay, because my thought has always been I'm looking at a weather front, and lately they've been coming down slowly.
Yeah,
I could look at the radar, and I do, and you can see they're going to get here or not. But
yeah, that's
so,
right.
but
As we'll see, a front is one way that an unstable atmosphere can get kicked off into a storm system, but it's not the only way.
wow,
So
okay,
you get a cold front coming through. We'll see how that can kick off thunderstorms. Usually a long line of thunderstorms that you can kind of see advancing towards you. But it can also happen on just hot days when there's really no front. And there's a couple other things that can kick it off as well. So we'll come to that.
Okay, thank
Question
you.
here,
Yeah.
when those balloons go up, the wind is effective where they are relative to where you launched them from. In other words, if I'm sitting on the Earth, sending a balloon up, the balloon is changing its position relative to where I sent it up.
That's right.
Is there any way on these SKEW-T graphs to know where that balloon is when it's sensing these temperatures and dew points?
Yes. So I don't have a way to do it right now, but if you went to that website that I showed you, this the sonderhub.org, you could actually track like it actually shows you the live track of these balloons as they're going up and they're wiggling around the points that they got launched from. The fact is they don't go very far. It takes an hour or two for them to rise. So they might move, if you think about it, worst case 50 or 100 miles away from where they've been launched. But more likely they tend to a lot of them circle around. They get blown one way for a bit, and then they get blown the other way for a bit. So it's kind of a random walk as they head up in the atmosphere. Um, so when you're looking at the raw data, let's distinguish two things. When you're looking at the raw data that the balloon is sending back, that's what you're seeing. You're quite right. It's at that place and time, not precisely over the spot from which they were launched. Once you feed that into the computer models, the GFS and the other the European models and things like that, what they spit out are their predictions over a specific place and time. So it's slightly different answer depending on whether you're looking at and these graphs I'm showing you are all outputs from computer models. They are not raw balloon data. There is no balloon that goes up over Bedford. I asked the tool to tell me what's the SKEW-T going to be over Bedford. So what we're looking at are the raw outputs of the big climate models or meteorological models that all of the weather forecasters use. Does that help answer the question?
Yeah, it helps. Thanks.
Sure.
You said one thing, you use the word probability. Are you going to talk about how the probability estimates are derived based on this data?
No.
Okay.
Just because I don't know. That's getting to a level that I don't
Fair
fully
enough.
understand. But good question.
That's a whole different talk. Fair enough.
Yeah, there you go. Um, another thing that we can look at, and we've got three different example SKEW-Ts on here, and this is obviously more of for a wintertime talk. We saw in our previous slide where we could discern icing in clouds. We can also discern different types of precipitation. So if we look at the SKEW-T on the left, this is sort of similar in that from ground level up to maybe a third or halfway up the chart, we've got a very close temperature dew point spread. So we know this atmosphere is going to produce clouds and probably precipitation with that much atmosphere in it. But we can also see that the entire plot from the ground up is at or below freezing. So this is a plot that's likely to produce snow. If we focus on the graph on the right-hand side now, again, we've got this very strong temperature, a very small temperature dew point spread, quite a long way up. But what we see here is what is a classic temperature inversion. So normally as we rise up in the atmosphere, it normally gets colder. But there are times when it gets warmer as we rise. That's called a temperature inversion. And that's what we're seeing here. The temperature on the ground on this, I'm looking at the right-hand chart now. At ground level, the temperature is maybe -5 Celsius, but within a few thousand feet, it actually rapidly rises to +10 degrees Celsius before it starts to cool off again. So that's a strong temperature inversion that can be caused by typically a warm front, maybe some warm air moving up from the south in the winter. And then it gets colder again. But because it's so moist, we're going to have snow falling from these upper clouds at around the 18,000 to 10,000 foot level. As they fall down, they'll encounter warmer air, and that snow is going to melt and turn to rain. And then in the last couple of thousand feet, it encounters cold air again, and it's going to freeze again. So this is a sounding that produces freezing rain and ice storms and all of our worst days of driving that we could see. And the middle plot is somewhere in between these two. You get a smaller, you still have that classic temperature inversion, but there's less time for rain or snow that's falling through the warm air to thaw and then refreeze. And what we get is then sleet. So something in between snow and sleet. So in the winter, if you see plots like this, and you see a temperature inversion, which is this classic, what they call a nose, the temperatures sweeping to the right and then back left again. That's where we can look for snow or sleet or freezing rain. So let's get to the meat of the topic and talk about convection, because the SKEW-T is also a really powerful tool to understand convection in the atmosphere. But in order to understand it, we have to do a little bit of go back to theory work and introduce a few new terms. The first of which is something called a lapse rate. And a lapse rate is simply how does temperature change as we move up in the atmosphere? That's what it means. And there are different kinds of lapse rates that we'll encounter. The first one is what's called the environmental lapse rate. So that is if I were to, it's what my balloon measures, where if you think about taking like an oven thermometer and you just stick it in the atmosphere at different heights as we go up, I'm measuring what is called the environmental lapse rate. And there is what is called a standard lapse rate. There is a standard atmosphere that we've defined because, God forbid, nature should just do its own thing. But there is something called the standard atmosphere, and it is defined as a surface temperature of 15 degrees Celsius, which is about, 62 Fahrenheit, I think, and a, quote, standard atmosphere, the temperature decreases by 2 degrees Celsius for every 1,000 feet that we climb in the atmosphere. And so, of course, it's never exactly standard. It's never that simple. But that is sort of what has been defined as the average atmosphere on a, quote, typical day, whatever that means. But just remember in this example that if it's a 15-degree day, what's called a standard day, at 5,000 feet MSL, it'll be 5 degrees Celsius. And by 10,000 feet above mean sea level, 10,000 feet, it'll be minus 5 Celsius. So at around 7,500 feet is where it gets below freezing on a typical, an average day. And just remember that 5 Celsius number at 5,000 feet. Now, that's if we were to stick a probe in the atmosphere or we measure it with a balloon. But what if instead of measuring the temperature, we were to take a parcel of air, think of it of literally like the size of a pillow or a bread box or something like that. I take a parcel of air from the ground and I somehow magically lift it up in the atmosphere. Well, when I do that, it's going to encounter an area of lower pressure. Never mind the temperature. I'm not going to allow it to exchange heat with the atmosphere around it. I'm just going to lift it up and I'm going to let it expand as it lifts up just because of the lower pressure around it. Well, as we saw, or as we know from our ideal gas law, when gas expands, it cools. And again, it's not cooling because it's moving into cooler air. It's cooling simply because it's expanding. And that's it's known as an adiabatic change. Adiabatic meaning it's not exchanging heat with the atmosphere around it. And it turns out, if you do the math, that if I take a parcel of air that's at 15 degrees Celsius at the surface and I lift it up 5,000 feet, it's going to end up at 0 degrees Celsius. And that's independent of the temperature of the air around it. Again, that's purely from the expansion and the pressure change. That gives us what is called the dry adiabatic lapse rate. It's the lapse rate. It's the rate of change of temperature with altitude. It's adiabatic, meaning it's only due to the pressure change, nothing to do with what the temperature of the air around it is. And it's dry, meaning I'm assuming I'm not cooling it to the point at which moisture is going to condense out of it. And that turns out to be a pretty constant 3 degrees Celsius for every 1,000 feet versus the 2 degrees Celsius per 1,000 feet that is the standard environmental lapse rate. So on an average day, theoretical average day, if I do this to a parcel of air, it's going to find itself colder than the air around it. Remember, at 5,000 feet, on an average day, it's typically 5 degrees Celsius at 5,000 feet. But my poor parcel of air that I've shoved up in the air finds it is going to be at 0 degrees. So it's going to be colder than the air around it, which means it's going to want to sink. And that's the definition of a stable atmosphere. If I disturb it, I take a parcel of air and I lift it up in the air, that parcel is going to want to drop back down again. It wants to return to its original position, which is the definition of stability. There is also something called the moist adiabatic lapse rate. So if that parcel of air was really humid and I lifted it up and I got it to a point where it met its own dew point, now water is going to start to condense out of it and it's going to form a cloud. But as it forms that cloud, it's going to release heat and it's going to warm that air up more. And so with moist air, if that water starts condensing, it actually creates a feedback loop that heats that parcel of air more. And that's going to be important when we talk about thunderstorms. The point is that the stability of the atmosphere is dependent on the environmental lapse rate. So in our standard atmosphere, this parcel of air is colder than the air around it, and it wants to sink. But let's say we have a day where the ground is really warm and it gets really cold fast as we lift that parcel up. Now that parcel of air may find itself warmer than the air around it. And so it's going to want to keep going. And that's an unstable atmosphere. If I take that parcel of air, and instead of wanting to sink back down, it wants to shoot back up, keep going up like a hot air balloon that's just shooting up in the atmosphere. That is what's defined as an unstable atmosphere. And that drives a lot of weather that we see, especially in the summer. Now, the world isn't full of mad scientists lifting parcels of air up in the air. So there are natural processes that cause parcels of air or air to get lifted. The big ones that we'll talk about are, number one, and particularly in the summer, solar heating from the ground. So the sun heats the ground re-radiates that heat back into the air just above it. It heats that air, and eventually that air gets buoyant enough that it just wants to pop up into the atmosphere. A second one is being blown up a mountainside. So if you think about a range of mountains and wind is blowing across those mountains, it's going to have to go up in order to get over the mountains. So that it's called orographic lifting, and that's air that's being forced up by being blown over terrain or a mountainside or things like that. And a third big one that Bob, you alluded to, is a cold front. And a cold front is a wedge of cold air, typically coming down from the north, because that cold air is denser. It's forcing its way. It's like the camel under the nose of the tent. It's sticking its nose under the warmer air, and it's forcing that warmer air up ahead of it. And so that's a third major cause of parcels being lifted. But now to relate this back to the SKEW-T, if our lapse rate, so the actual temperature that is being measured, is decreasing very rapidly as we climb, we're going to have an unstable atmosphere. And in fact, if it's a very heavily left-leaning temperature curve or temperature line that's in this red zone, then we know that the atmosphere is definitely going to be unstable. For a pilot, that means it's likely to be turbulent, but it's also going to drive certain weather formation that we'll talk about in a second. On the other hand, if that line is vertical or leaning to the right, that atmosphere is stable. That parcel of air is going to find itself in warmer air than it is, and it's going to want to sink back down. And so we talked about temperature inversions earlier. The temperature inversion, it goes to the right. Temperature inversions are always stable. This shows up on days, where you get smoke or haze trapped at the lower level. And you see just a band of, particularly with wildfires, you see that layer of smoke and it's not going anywhere. High pressure areas tend to be stable because what high pressure is cold air descending in the atmosphere. And it's pushing down and creating a cap on top of the air that's already around, and that creates stability. Conversely, low pressure areas tend to give instability because a low pressure area is an area of rising air. And then in between these two lines, so between the blue and the red line, is what's called conditional stability or conditional instability. Because is that air going to be stable or unstable? The answer is it depends on how much moisture is in the air. If that air is very dry, it's going to be stable. If that air is very moist, it's going to be unstable. And that's because of that energy feedback loop that we talked about earlier. So that's what I just said. So what does this look like? Let's actually look at some pictures. So here's a nice typical summer day. And this will be a day where there's a modest amount of humidity in the atmosphere, but it's a warm day, so that sun is heating the ground. It's lifting as that ground gets hot, it heats the air above it. That air is going to rise. It initially rises at the dry adiabatic lapse rate. That parcel's being lifted and it's cooling off at the dry adiabatic lapse rate. But at some point, depending on its humidity, it hits its own dew point, and the moisture starts to condense out, and we get clouds. And what we get are these nice, beautiful, puffy cumulus clouds. And we know that these are cumulus clouds, or a couple of characteristics of them. One, you'll notice they've got flat bottoms, and that's because all the air in this area is roughly the same humidity. So it all condenses at about the same time as it's rising. And they've got puffy tops to them, like muffins, because that air, it's right. You can actually visualize. This is a direct visualization of what's happening in the atmosphere. So that air is rising from the ground, condensing at the flat bottom of the cloud. It's got momentum, so it continues to rise for a bit. And as that moisture condenses out, it releases heat. So it continues to be warmer than the air around it and continuing to rise, continuing to cool, and giving up more and more of its moisture until eventually it runs out of steam and we get these nice little cauliflower tops on top of our cumulus clouds. So, this is like just direct visual. You can actually see what's happening in the air very directly with this. Supposing it's a hotter day now and it's more humid and this process keeps going, eventually it's going to turn into something like this. This is called a towering cumulus cloud. So this cloud is getting taller and taller. Again, this is just visualizing that plume of warm, moist air rising from the ground with a puffy top. And if you're a pilot, you avoid these clouds because they're going to have a lot of updrafts and downdrafts in them. So you're going to want to fly around these things. And this is true. These clouds could go pretty high. They could interfere with jet traffic as well. And on days like today, particularly planes that are descending into Boston or, big, and I'm talking big commercial planes here, they'll be making deviations around these sorts of clouds because you'll have a very bad ride if you fly through these things. So that's a towering cumulus cloud. Now, if you're having a really bad day and there's a ton of moisture in the air and a ton of heat, and this thing just wants to keep going, it's going to keep going until eventually it hits the top of the troposphere and hits about 30, 40, 50,000 feet. The nature of the atmosphere changes. The temperature starts to stabilize on any given day. And that moisture is going to start to spread out and form a classic anvil cloud, which is what we see here. The moisture eventually is also going to start to fall back down through that cloud as heavy rain. That moisture can then get caught up in the updrafts, the strong updrafts from the rising air, and get lifted and fall and lifted and fall and lifted and fall through the freezing level, which is what creates hailstones. That lifting and falling and all that convective mixing like a washing machine produces a lot of static electricity, and that eventually shows up as lightning. So this is the process that creates thunderstorms. And this is a classic thunderstorm cloud, a cumulonimbus. And we definitely don't want to be flying in these, and we don't want to be underneath them either, because lots of weather happens underneath these things. Hail, rain, lightning, thunder, massive turbulence. From an aircraft point of view, the most dangerous thing about thunderstorms is actually the turbulence, maybe the hail as a secondary effect. Lightning can be a problem, but planes are tested to withstand lightning. It shouldn't affect them. They're basically Faraday cages, and lightning just goes through them. But it's the turbulence that is the real killer for aircraft in thunderstorms. So you may think if you're a nervous passenger that you flew through a storm. I promise you, you didn't. The pilots went around it, and occasionally they can go over it, but sometimes these storms can go up to 50,000 feet, and there's no aircraft is going over that. So let's come back to the SKEW-T. So what does a thunderstorm look like on the SKEW-T, and how do we start to interpret these graphs to tell us the likelihood of thunderstorms? So this is an example. I actually pulled this one. It was in January, so there were no thunderstorms around here. So I had to go to Brazil to find a sounding that was a thunderstorm sounding in January. But this is a classic thunderstorm sounding. So let's just pick this apart a little bit. Let's start at the ground. We can see that the temperature at this particular place and time was almost 30 degrees Celsius, so about, in the mid 80s on the ground. Not super humid on the ground, at a dew point of around 20, so humid, but not horribly so. But a couple of features just to point out on this graph. The first is there's this little temperature inversion. You can see the red line just leans to the right as we start to climb up. And that's really important because it creates a cap where pressure can build up beneath it. And that's important, if that building up of pressure is something that is important to create the conditions for a thunderstorm to form. And then it starts to lean left pretty strongly. So we know we've got an unstable atmosphere above it. And this is where those adiabats, these additional diagonal lines start to play. So the line I've now drawn on top of this shows the path of a lifted parcel of air starting at the ground and moving up. But let's really focus on the air above this 950 or 850 foot millibar. If I were to take this parcel of air, my pointer's not showing up, but I'm looking at where at the bottom of this red hatched area, if I were to take a parcel of air at this point and lift it up, we can see that it's going to follow this is moist air. It's going to follow the moist adiabat. It's going to follow this purple line all the way up. And so we can see that it is going to be warmer than the air around it because its temperature is going to be warmer than the lapse rate as measured by the balloon, which means it's going to be super buoyant. It's going to want to keep rising, and it's going to want to keep spitting out moisture as it goes up. And in fact, the area between this purple line and the red line, the fatter that area, the more extra energy it's going to have and the more buoyant it's going to be because it's going to be warmer and moister than the air it's rising into. We can actually measure this area into something called the CAPE. The CAPE which is this number that you can see top right. That's calculated by the computer. But the CAPE stands for convective available potential energy. It's how much energy is loaded into the atmosphere. And anytime you see a CAPE above about 1,000, we're looking at thunderstorms. I'll characterize what that number means in a little bit, but this is a classic thunderstorm sounding. So anytime we see this left-leaning, the combination of heat and moisture and a left-leaning lapse rate, we know we're in trouble with thunderstorms. And if the tool we're using shows us our CAPE, and that CAPE is over 1,000, we know we're likely in for storms. And the bigger that number, the worse the storms are going to be. We talked about all of this. Okay. So finally, let's look at just like there are classic photographs, and there are certain photographs that you look at that are iconic and you recognize them as, oh, that's the kiss on VE Day in Times Square. This is the kiss on VE Day in Times Square to a meteorologist. You can show this graph to a meteorologist. They'll go, I know what that is. So this particular SKEW-T has become famous or notorious. And this was 2013. You can see the date top left. 2013, May the 20th at 1700 UTC, which is about noon Central Time in Norman, Oklahoma, which is where the Storm Prediction Center is. And a meteorologist will take a look at this and go, uh-oh, we've got trouble here because it's got all of the elements of what is called a loaded gun sounding. It's fairly hot, not super hot. It's 81 degrees or 30 Celsius at the surface. It's rapidly unstable, so this extreme left-leaning line lower down. Then there's a temperature inversion where it gets warmer for a bit, and then it gets again very unstable again. The CAPE, that potential energy on this presentation, we can see it down at the bottom left. The CAPE at the surface was almost 5,000. The units, and I said anything over 1,000 was a problem. This is 5,000. The units of these are joules per kilogram. So this is how many joules are available of potential energy per kilogram of atmosphere. If you go and do the math about how much the atmosphere weighs in, let's say, a 10-mile radius going up, and you multiply this out by joules, you get a number of joules that is roughly equivalent to a small nuclear bomb. Literally, it is kilotons of TNT equivalent loaded of potential energy in this particular sounding. So this is going to be a big one, and you can just see that. So what did that turn into? Like, how did that progress during the day? Remember, this was at noon. Well, here's what that looked like 3 hours later. This is the radar around Oklahoma City. It looks fair. Not only does it look bad because there's lots of red and purple, but it has this characteristic hook shape if you look at the bottom of the middle of the radar returns, you get this swirling hook shape, and that's characteristic of a tornado. So this is the kind of sounding that generates not only thunderstorms, but tornadoes. And you can also, it's a little hard to see on this diagram, but you can, with the wind direction, you can start to see the vorticity or the turning that's happening in the atmosphere that begins to set up the conditions for not only storms, but storms with that spawn tornadoes. And here's what that looked like on the ground. So this was Moore, the town of Moore, just south of Oklahoma City, that evening or the next day. And you can see the path of this EF5, one of the strongest tornadoes ever recorded, that ripped through the town of Moore. It goes left to right on this picture. You can see intact houses and buildings at the top of the picture, intact houses and buildings below the road, but this just path of destruction left to right as that tornado tore through that town. Did somebody have a question? Okay, so I'm going to close out. If this was interesting, great. Here are some resources that you can, I'm happy to send this presentation to someone so it can go on the website. But there are different sources that you can get SKEW-Ts from. I showed you flytheweather.com. There are some others as well. There is also a whole wealth of literature on how to interpret these things, and here are a couple of sites where you could do that. There are literally whole undergraduate courses on this stuff if you want to get super deep, but you don't need to do that. With a little bit of understanding, I think, for me anyway, understanding these things has helped me understand what's happening locally, helps me plan my flights better. But I can also be confident, if the neighbor says, are we going to get storms today? I can be more confident than the local weather person to say, yes, we are, or no, we're not, simply based on a quick look at a SKEW-T diagram. And that is it. Thank you so
Back
much.
to the Norman, Oklahoma film again.
Yeah.
It only looks like it's about, I don't know, a couple of blocks wide.
That's right. Yeah, tornadoes. I mean, a tornado is an incredibly tight vortex of nastiness and death. So while there were widespread thunderstorms going on, the core of the tornado, I mean, you've seen movies of tornadoes, right? They're narrow, but they have winds of 200 plus miles an hour within them.
So if you're a weatherman looking at those maps, how do you get the word out, and where do you send the word to?
So you'd look at the radar. First of all, this would give you a few hours warning that, a sounding like this would produce a tornado watch. We are going to get tornadoes in this area somewhere this afternoon. Exactly where? I have no idea. This doesn't tell you that. Then you start to look at the radar picture and you start to see the vorticity, the swirling at certain points. And now you can get more precise about where, to issue a tornado warning, which says, This is where it's likely to touch down. But that's about as good as you can do. Nobody, we don't have the ability to predict it's going to be precisely at this point. We have it within 10 or 15 miles and maybe, plus or minus 30 minutes. So that's sort of the range of
The
area.
other day, one of these warnings came up on my television,
Yeah.
and it said, warning for Middlesex County, thunderstorms, tornadoes, whatever it said. And then especially the following towns.
Mhm.
And the towns were in Worcester County.
Yeah.
So it said, warning for Middlesex County, and here are the towns. And the towns were in Worcester County. How does that make any sense?
I can't tell you. Poor grasp of geography by TV stations. Shocking.
By the U.S. Weather Service, they have the capacity to interrupt every once in a while. You get the test. It was from the U.S. Weather Service. It was not from some not from some television person.
Yeah, I don't know what that process is. Clearly not perfect.
And if you look at this radar, this is a static picture.
Yeah.
But you do have a time lapse picture of the same area, correct? That's available to you today, these days?
Sure. Oh yes, absolutely. Yes,
So
you can see this develop over time. Absolutely.
Right. So using that, can you look at the direction of the storm in general, the steering direction of the storm, to
Yes.
give you a better indication of who's in the crapper and who's not?
Yes, absolutely. And you can see that again, the SKEW-T projection, if we go back to this one,
Yeah, the winds show you.
this is observed, but we can also do predictions. And, it will predict what the winds aloft or the winds at different heights are doing. And so it's typically the winds around the 18,000 foot, the 500 millibar mark are the big steering winds that tend to move these systems around. So you can look at what that's going to do, and that's going to give you, the radar. The radar is historic and is historic. And in fact, when you look at a radar image like this one, that's always about it takes time for the physical radars dotted all over the country to acquire the data. It takes more time for a synthesized picture like this to be cooked. And so radars are always, best case, 15 minutes behind reality. When you see a picture like the Doppler radar that you see, it's never live. It's about 15 minutes old. And it's historic. It might show me the last hour. So I can see trends, but a radar is not predictive. The models are predictive.
And so going back to the SKEW-T, it looks like it's moving from the southwest, correct?
Correct. Yeah. Yeah. But, you'd look at,
and you have the speed there indicated. So you have a general idea of how fast it's moving in what direction. The vector that you can look at.
That's right. But remember, this is one point. If we go back to this picture, this shape suggests that there's and we'd know this from other observations. I don't have all the context, but the fact that this is sort of in a line suggests that there's a cold front involved as well. So my sounding in Oklahoma City or in Moore might show me that the winds, and this happens quite a lot, the winds south of the front might be moving from the southwest, but the winds north of the front might be moving from the northwest and colder. That's what is actually producing the lifting effect that's kicking this whole thing off. And in fact, it's that shift in wind from southwest to northwest that provides that rotation that is kicking off this particular storm.
Adam, going to this point about wind, I'm trying to understand wind, which is a horizontal movement of air, to my mind anyway.
Yep.
From SKEW-T graphs, is there a way that I can understand both the velocity and the direction of the wind from these graphs?
Yes, absolutely. So this is one presentation. If we go all the way back, well, actually, this one shows it as well. The right-hand side of the graph actually shows exactly that information. This one's kind of wimpy. Let's go back to my example much earlier in the presentation. Yeah, so this one. So you see these this line of red pennants up and down the right-hand side of the graph. that is showing me wind speed and direction by height. And the way to read this is all of these winds are generally coming out of the southwest, but it's more southerly lower down and it's more westerly higher up because of the direction of these little arrows, the way they're pointing.
So that's a separate measurement. It's not dew point and temperature.
It's wind speed and direction.
It's actually a measurement of the movement of
Yes.
the cone.
That's correct.
On that. So it's a separate.
Can I share my screen, Adam? I have the Fly the Weather up.
Yeah, absolutely.
So I can't calculate from dew point and temperature anything about wind. Is that correct or not?
That's correct. The dew point and temperature is all about the vertical, what's happening vertically, and then the wind is what's happening horizontally. And that's
what if I take a number? What if I were to send a number of balloons up at the same time and only measure dew point and temperature? Could I then, from relating those measurements from balloon to balloon, say anything about wind?
Indirectly, you could, but I'm not sure why you'd bother when you can measure wind directly with them. So what you would do, what that would tell you, and it does tell you, is what the well, let me think about this.
You didn't look at the pressure gradient just to compute the wind.
But that only works if you know your altitude. So
yeah,
what these balloons, right? But the way they measure their altitude is with pressure. So you need some other way to measure altitude, like with GPS. If you are measuring your altitude with GPS, then you could measure pressure gradient, and then you could build a model that shows, you're right, isobars and pressure gradients, which is actually what drives winds.
So Adam, let's can you see what I'm presenting here?
Yeah.
This is from Fly the Weather. This is based on the Bedford 1500 UTC, which is 11 a.m.
Right.
Okay. It shows that the temperature along the red line, the dew point is below the temperature. I don't know what the purple line is.
So the purple line is the path of a lifted parcel of air right now.
Okay.
And so what it's showing me is if I were to lift a parcel of air right now, it's going to cool off. And if you look at that initial left hand, that little bit, that's the dry, the dry air being lifted. Where it makes a little right hand kink, right where your cursor is now, is where that air is going to condense and start to form clouds. So what this is telling me, and in fact, on the right hand side, it shows there's a number called LCL. Do you see that? Where it says 5137 feet. Yep. That is a prediction that we're going to have some cumulus clouds today, starting at 5,000 feet. It's called the lifted condensation level. And so it's
going up.
And it's going up. So the clouds should get a little bit higher. As what this is telling us is the clouds are going to get a little bit higher as the day goes on. We can also see we've got a cape of 70, so that's very low. So no chance of storms today. So this looks like a nice sunny day with some puffy clouds that will gradually disperse during the day.
And this is the wind information at those different levels here.
Exactly.
Where this is for the one I'm showing right here is coming out of the south-southwest at about 15 knots.
Perfect. You've been paying attention.
Yeah.
We have this guy over here. This is the Sonde hub.
Yep.
And it shows.
Yes, if you click on one of those balloons, maybe the one over Long Island.
This one here.
Yeah. If you click on that. No, actually click on the balloon.
This here.
Yeah. You click on it. So you can see there's the path that it followed as it rose. That purple line.
This here.
Yeah. Mm-hmm. So there's where it was launched, and as it rose up, it's been drifting around, and it's currently on the top left-hand side. You can see its current altitude, its maximum altitude, what it's, and in fact, there's a little SKEW-T button. So if you just down to the right of where your hand is, no, back in that left-hand box, go right a tiny bit, SKEW-T, there you go. We can actually hopefully see the live. There you go. There's the live data coming from the balloon as it was rising. It's pretty cool.
Oh, it's getting really cool.
Yeah. Yeah.
Mm-hmm.
And while we're at it, this is weather.com, and this shows the current weather And if it's working, it will show.
It'll show the historic radar loop. Yeah.
Yeah.
And this guy does it as well. And here you can see where the weather is down around the
Yeah.
area. And then
Wind,
Boston here has
windy,
another one.
windy.com is a great site as well. And that has a ton of deeper weather tools that you can get from sort of more more what's the word, sort of accessible or kind of public friendly websites
When it works.
when it
So Adam,
works. Yeah.
you're filing your flight plan. You go through all these 18,000 different sites and figure out what you want to do?
It depends. So it depends on kind of how marginal the conditions are. Like if the forecast is like it's just going to be a bright sunny day, I'm not going to dive into this stuff because there's no point. If it's going to be a blizzard, I'm just not going. Or we just know there's going to be a ton of thunderstorms. I'm just not going, so I don't bother. But it's on days where it's marginal. I definitely dive into this stuff because it helps me make better decisions. So, for example, there was a flight a few weeks ago. I do a lot of volunteer flying. I was taking a patient up to Presque Isle, and the generic forecasts and even the specialist aviation forecast said there were going to be thunderstorms, or there was likely thunderstorms up in Maine that afternoon. And I went and pulled the soundings, and the SKEW-Ts were like the Cape was at like 700. Like, there's not going to be storms, and I could tell that. And I flew it, and there were no storms. So on days when it's marginal, it can help you make a good decision where the generic sites don't. So that's how I use it.
Cool.
Thank you.
So these packages are getting launched with actual helium balloons and a package of instruments every day from a lot of these sites around the US.
92 sites, 69 sites in the continental US twice a day. 92.
So like a lot of them just fall in the ocean, or do they just kind of
Yeah, they fall back, and they have a mailing. If you find one, if they have a mailer attached to them, and you can send them back if you're a good citizen, or you can keep it as a souvenir. I saw a statistic.
Will they ever switch to UAVs?
No, because these things go up to 100,000 feet. No UAV can go that high, and these are dirt cheap.
What's a UAV?
Drone.
Like a drone.
Unmanned.
That would go out and come back, and you wouldn't have to go like wait
Yeah,
for it to be.
but a drone can't. There's no drone. I don't think there's an unclassified drone that can go to 100,000 feet regularly and cheaply.
Mars, so
but not cheaply.
So Adam, just out of curiosity, the size of the package that they use, I mean, the picture you showed of the instrumentation package, is it inches? Yeah, yeah. That's
It's a little plastic. It's a little plastic box with a battery and an antenna and a few sensors. And they cost tens of dollars.
Yeah, interesting.
Did I understand correctly that we're using millibars and all metric units for temperature and feet? Is that right? Thousands of feet? How did we? Is that only in the US? The Europeans can't be doing that, right?
No, the Europeans do it in meters, of course. They use millibars and meters, or actually, technically, they use hectopascals and meters.
Got to go all metric. Come on.
Yeah,
I would hate to see the units for things like Cape or something, right? Where it's
that's joule. Actually, that's joules per kilogram. So that's SI.
Okay, so the feet don't come into play there, huh?
The feet are just for pilots' convenience because that's how we think.
I see.
That's American pilots think like that. European pilots think in meters.
It depends. Actually, no. In many cases, most of Europe actually uses feet for aviation.
Wow.
Russia doesn't. Russia uses meters.
So I was thinking, pilots that fly transcontinental, they go, I'm sorry, intercontinental, where they go from Europe to the United States or Asia to the United States, they have to understand feet because that's what we use. But if you're flying totally in an area like within Europe, feet don't mean a damn thing, right?
Mostly Eastern Europe and Russia use sort of obsessively use meters, but if you're in France or Germany, they use feet.
Now, Adam, if you're flying in the United States and they say you're flying at flight level 10, that means 10,000 feet. Is that right?
Uh,
Oh, no.
we're opening up a can of worms here. So a flight level is so the short answer is yes. Add flight level 10 would be 1,000 feet.
Oh,
You
okay.
add two zeros to it.
In
Every
Europe,
country.
would they use flight level 10? Would that be 1,000 meters?
No, it would still be feet. It would be 1,000 feet.
Okay.
Still, difference between a flight level and an altitude is the way planes set their barometers change at a particular altitude, and it's different by country. So in the US, everything below 18,000 feet, we talk about feet, and everything above 18,000 feet, we talk about flight levels. So 23,000 feet would be flight level 230. And it comes down to how high, what's the highest mountain in that area is what drives it. But it's a whole other topic.
So somewhere on Hanscom, there's like a giant tank of helium that's maintained by NOAA. Is that
Well, they
about
don't
right?
launch them from Hanscom, but somewhere on the Cape there is, yes.
Oh,
Yeah.
okay.
Yeah,
Okay.
yeah, the examples I showed were all model outputs. They weren't actual balloon soundings.
Those were simulated.
Those are simulated. Yeah, but yes, somewhere, yes, they have tanks of helium that they ship around.
You said Chatham was the launch site, or Chatham historic launch site?
It's a little north of Chatham currently, but something happened. I think it fell. Maybe it got eroded and fell into the sea or something. It was somewhere on the Cape near the.
In Easton or Brewster.
Yeah, something like that.
Easton.
I don't know precisely.
So you're saying
It says north of Chatham.
well, there's
Yeah.
lots of towns north of Chatham.
There's the ocean north of Chatham. You go too far.
You got Eastham, Truro.
That's east.
Town.
It's somewhere on the outer Cape.
Yeah.
I think launches have been suspended. I heard because the launch site may have got eroded into the sea, so it must be on the outer side of the Cape. And they were planning to move the site to Chatham Airport, but that hasn't happened yet. That's my understanding of what's going on at Chatham.